To understand the C language, you have to understand pointers. A pointer holds a virtual memory address to the first byte of a value of a specific type. The CPU and operating system map that virtual address to the underlying resource, RAM, a file mapping, or a device register. So dereferencing the pointer reads from or writes from whatever is mapped there. Every process on the OS sees a private continuous virtual address space, which gives isolation. Processors can't see each other's memory. The numbers in pointers are virtual addresses. They haven't directly corresponded to physical RAM since the Intel 386 in 1985. Mainframes had virtual memory since the 60s and 70s. We think of memory as RAM, but starting in 1961 with the Manchester Atlas, whatever, they invented virtual memory, and all the famous computers like the PDP and the VAX on the mainframe, they had virtual memory. So when the Intel processors going for home computers, instead of having a big mainframe, you could have a computer at home. I think the 286 was definitely 16-bit, and then the 386 was 32-bit, and that was the first time that serious things happened, where forms of Unix like BSD and then Linux were ported to that, to the 386, because it had virtual memory, it had paging, it had a memory management unit on the hardware. So that's when the real operating systems came to home computers for the first time with the 386. That's what Linus Torvalds wrote Linux on. The CPU's memory management unit, MMU, uses a table maintained by the kernel to translate virtual pages, e.g. 4 kilobyte blocks, into physical frames in RAM, or into other backings like files or device memory. So you can think of it as RAM, but it hasn't been RAM since 1985 in Intel and since the 60s and 70s in mainframes. So it's actually a virtual management system that the operating system controls. To use memory in C, you have to ask for it. So let's look at some C code. Firstly, we have the imports. Standard in-out and standard lib. They are very common imports that you get, probably the top of most C files. Unlike in Python, where the name represents what it is, you just have to learn by convention what the names are, what to import. When I used to do a lot of C programming, this was like pre-Stack Overflow, obviously pre-AI, pre-anything used to be on the internet. We used this book. You use various books. So this was my favourite book back in the day, which was called The Linux Programming Interface, a Linux and Unix System Programming Handbook. And it's a fantastic book because it explained everything, basically everything you'd ever want to do in C is in here. Oh, there's something in here. It's a payslip. 31st of March 2015. So 2015 was presumably maybe the last time I read this book. Might have done some serious work in C. 2015 maybe was the last time I did really serious work in C. Professional work in C. Just 10 years before writing this video. Recording this video. So anyway, but this book is brilliant. It has everything you'd ever want to know about programming C was in here. So it had different chapters that basically explained how to do everything you'd ever want to do in C. It was brilliant book. It's one of those like 14,000, 15,000 pages, but it's one of those brilliant books that, as a professional writing code, you just had everything you needed. That was heavy. Go to work carrying this around all day. Heavy thing. Standard in out gives you the print function and other things, and standard lib gives you malloc and free, and then the most important, the memory allocator, and then free the memory, the most important functions in C. We start with the return type, which is int, we're going to return an int at the end. When we're done, we're going to return 0 to say we're done. And then, so then we declare a function. So we're going to allocate space for one int in memory. So we do int, so that we know it's an int, and then we do star, so we know it's a pointer. Then we name it. I've just named it P. Then we do the memory allocation, and we give it enough memory to be an int. So the size of an int could be different on different computers, different platforms. So you do size of, and that gives you the size. You don't hard code it. You do size of, and it works out the size. So that returns a pointer, and a pointer, if you remember, is a virtual memory address to the first byte of a specific type. So that's where we're going to store our data. So if you store a lot of data, you need to know how long the data is, so that you can start reading from there, and then you just keep chugging through the memory until you get to the end of the data. And if you keep chugging beyond it because you haven't set the size, then in an old system it would read some random memory, it could have some memory of a different program or something. But in the modern system, it will just kill your program. The operating system like Linux or Windows will just say, "Hey, it's doing crazy stuff. Let's kill this program." So it's very important that you read and write from the right places. So now we're going to write the number 123 to that memory, and then I'm going to show you where it is, what the address looks like, and then we're going to read it back through the pointer. So to read it back through the pointer, we dereference it with the star here, and that will turn it. That will go get the thing, and then we're going to read an int's worth, and print does that for us, and then we're going to free up the memory, and then we're going to end the program. So the way you run a C program is you normally make a make file, but also which will then, the make file is like a configuration file that you run, and it will then call GCC, and it will go something like example and then output to example, and then that makes a file called example, which is a binary file which might blow up VS Code, but let's see what happens. Okay, it just comes as a load of red noise. So that makes the binary file. That is the program in machine code. If you don't do -o, then by convention it calls the executable a.out. So you see now we've got one called a.out. So we'll delete that anyway. So, and in the modern world as well, you don't even have to run GCC anymore, because I think if we just press play here, Microsoft Visual Studio Code will just run it. Although a bit noisier. Anyway, it makes all this noise. But anyway, so let's just show us running it. It prints the pointer address, which is here. So P gives the pointer address. But if you do star P, it then gives the location of the thing stored at that pointer, which is that. Hopefully that made sense. There were some kind of academic languages that had automatic memory management, like Lisp and Smalltalk. But Python felt revolutionary in the early 90s to the kind of real engineers, kind of working engineers who got it. Python was the one that kind of broke through and felt revolutionary. I mean, some of the concepts were elsewhere, like there was an interactive interpreter in Tcl. Perl was just coming out. Python kind of combined the best ideas from kind of leading languages of the day, made it very approachable and clean looking. So with Python, you don't need to learn memory management. You just get a shell, and you can just start typing things. I mean, just doing that, not having to compile it, not having to know anything, was really revolutionary in in the early 90s. I mean, since every browser has JavaScript and kids learn by opening the console and typing things in, it doesn't seem as revolutionary. But in the early 90s, this like immediate language was a big improvement on what went before. You didn't have to know or care about memory management. You could just stick this in front of people and it would just work. They could just type code. It kind of harkened back to the kind of BBC Basic on the 8-bit computer era, but in a powerful object-oriented language for the 32-bit era. Now coming full circle, even though in Python, on an introductory level, you don't need to know any of this stuff, it does actually help at a more advanced level understanding the C language and understanding pointers. So before we pointed out that our 123 that we stuck in memory has a pointer address. If I go into Python, A is 1, 2, 3, then that A is actually a pointer. You see, that's a pointer, that's a pointer. It's exactly the same. This A uses, in the implementation of the Python references, it uses pointers. So A is pointing to this list stored at this memory location. And we know it uses pointers because if I have two lists and I append 4 to the first list, it's appended to the second list. So A and B are both pointers pointing to the same memory location where this list is. If I show you with a dict as well, like so X and Y are both references pointing to the same memory location. So even if I assign X to something else, so X is now Boo, Y still points to the dictionary because all I've done is I've repointed this reference to something else, but what's in the memory location at so what's in the memory location is still the same. So back to my A and B. So I do see they're both storing the same memory location. A and B are still storing the same memory location. So even though when I reassigned X here, Y was still pointing to the memory location. So I hadn't lost the memory location. If I now reassign Y, then this will then be dangling in memory and Python will clean it up. The garbage collector will just clean it up. But for now, because I still have this Y, this still exists in memory. I hope you learned something. That's enough for today. Come back for more tomorrow.